Gen Chem 1. Another Chapter 4 lecture. In this lecture, we'll cover aqueous solutions, the process of dissolving compounds in water, and the electric properties of such solutions. You'll find the material in section 4.5 of Tro's textbook. So let's jump to it. You should know that aqueous solutions are those where water is the solvent. When a solid is added to water, it may or may not dissolve, but what happens is the attractive forces that hold the solid particles together in the solid phase end up competing with the forces of interaction between the water and the solid. If it does dissolve, then the solute particles become separated in solution. So in the solid phase, all of the solute particles, or all of the solid particles, are together, all packed together, but in solution, they're all separated and dispersed in a homogeneous fashion throughout the water. For example, sodium chloride added to water. We know this does dissolve from experience, and you could write the chemical equation as sodium chloride solid with water yields sodium chloride in solution. So what about these attractive forces and the interaction forces between water and the solid? What's going on there? Well, let's look at the reactant material, the sodium chloride solid. So here's a pile of salt. If you examine one particular crystal of salt and you look at it under a microscope, you'll see it has a nice cubical structure, and you might even see a bunch of cubes stacked together. And these cubes, believe it or not, go all the way down to the atomic level. So if you examine sodium chloride under X-ray crystallography or something like that, that allows us to see the positions of the particles on the atomic scale, they're all nicely and cubically arranged. So here's one of those atomic level sized crystals that's cubic. What you'll notice is that the sodium cations and the chloride anions alternate with one another throughout the entire crystal in all three directions, X, Y, and Z directions. They have a nice order to them, nicely lined up. That's something about crystals, a very ordered structure. Particles are closely packed together, and the reason they're packed together is because all of these particles have interactions with one another. Without interactions, you would not have a solid. So the interactions are, of course, the opposite charges attracting each other. If you look at any particular sodium cation, it's surrounded by chloride anions, and every chloride anion is surrounded by sodium cations. And these interactions between the cations and anions are ionic interactions. You see, sodium having a plus charge is missing an electron, and the chloride has an extra electron. And so the interaction between a positive ion and a negative ion is that of opposite charges. It's an electrostatic interaction, and it's very strong. So how is it that this structure that's held together through very strong interactions is able to dissolve in water? Because as soon as it does, all of these particles, all of these ions become separated from one another. Well, the water is able to rip it apart, basically, because the interactions of the solute particles with the water are stronger than the interactions of the solute particles themselves. You see, there's a competition between the interactions of the solute particles among themselves with the interactions of the solute particles with the surrounding water, and it turns out that those solvent-solute interactions win out, and that's what allows it to dissolve. So when it does dissolve, all of the ions are separated from one another, and we can even rewrite this chemical equation acknowledging that the cations and the anions are separated in solution. This is called the Ionic equation. When ions become separated in solution, that's called dissociation. The particles of the salt, the ions, become separated. So when ionic compounds dissolve, we say that they dissociate in water. It turns out that the ions that are now floating around in solution give this solution a nice property. It conducts electricity, and we can call this solution an electrolyte. So electricity can pass through a saltwater solution because of the presence of the ions. We'll talk about electrolytes and how they operate on the next page. But first, what about these interactions again? How is it that water is able to rip this compound apart and cause all of these ions to become separated? Well, if you look at water molecules, they have a nice triangular structure. The two hydrogen atoms are connected to the same oxygen atom, and it's a kind of a triangular structure. Now, water molecules are polar. The oxygen right here pulls electrons closer to its side of the molecule. There's something special about oxygen that allows it to do that. So you see, oxygen is connected to hydrogen through covalent bonds. They're sharing electrons between them, but oxygen kind of pulls them to its side of the bond. And same thing over here, it's pulling the electrons between it and this hydrogen, to its side of the bond. And it's that special nature of oxygen. And because of this, this side of the molecule that's closer to the oxygen ends up being kind of negatively charged. Not quite a full-on minus charge. It's not like you have a minus charge over here and a plus charge over here. It's sort of like it's almost a minus charge. It's a partially charged end, and that leaves the other end of water where the hydrogens are partially positive. And so this is a polar molecule. We'll discuss the structures of molecules and their polar nature more in Chapter 9. But for now, we can just see that because this molecule is polar, how it is able to pull apart certain ionic compounds like sodium chloride. You see, what happens when you take this crystal and you put it in water, you have water molecules all around this crystal now, and they're basically going after these ions. Every single cation now has a bunch of water molecules around it that are interacting with it, and the interactions are quite strong as well. In fact, it does dissolve. Water is able to pull these ions apart from each other, and so in solution, all of the cations are surrounded by water molecules with their negative ends pointing towards them. And likewise, all of the anions are also surrounded by water molecules, but this time with their positive ends pointing towards them. And there are lots of these ion dipole interactions. That's what they're called. Ion dipole interactions. Many strong interactions between the ions and the dipoles on the water molecules. And that's what allows water to pull it apart. Let's look at another example of a compound that we know dissolves in water, and that's table sugar, or sucrose. When sucrose is added to water, it does dissolve. We know that from experience, and therefore we can write the process by this chemical equation, C12H22O11 in the solid phase with water yields the compound dissolved, aqueous phase. Now this time it's a little different though, because sucrose is not an ionic compound, it's a molecular compound. So the particles this time are molecules, and when it dissolves, all of the molecules become separated from each other. So the particles of the sucrose, the molecules, become separated in solution. There are no ions, and this would not conduct electricity. It's called a non-electrolyte. If you were to examine some sugar crystals, so you pick yourself out a sugar crystal, you would still see a nice crystalline structure in which the particles are tightly packed together with a very high degree of order in all directions, but they're not held together through ionic bonds. These molecules are held together through dipole bonds, kind of like water molecules. So if you examine one particular molecule of sucrose, I have its structure right here. Let's take a closer look at this. Lots of atoms, 12 carbons, 22 hydrogens, 11 oxygens, and this is called the Lewis structure of the molecule, and we'll again look at these things more in chapter 9, but this tells you how the atoms are connected together. So this carbon is connected to the hydrogen here, hydrogen there, carbon here, and oxygen there. But anyway, there are lots of oxygens in this molecule, and oxygens have that special ability to draw electrons towards their position. And so this large molecule has lots of negatively charged regions, or partially negative charged regions, and there are in turn other parts of the molecule that are partially positive charged. So this molecule has its own electrostatic character, and that's kind of why the molecule packs together in the solid phase. The molecules pack together because one molecule and another molecule kind of interacts. The partially negative regions over here interact with the partially positive regions over here, and they kind of interact. They're called dipole-dipole interactions. And when you take a piece of sucrose and you add it to water, again, water molecules all around it now, and the water molecules interact with these sucrose molecules through dipole-dipole interactions between the water and the sucrose. Okay, and you can imagine a sucrose molecule all of a sudden having 100 water molecules surrounding it, and the water is interacting with the partially positive and partially negative parts of this large molecule, and it's able to pull it away from the crystal. And once it's pulled away from the crystal, all of a sudden you have water molecules all of the way around it, and it's stabilized in solution. So again, it's a competition between the interactions of the solid particles among themselves versus the interactions between the solid particles and the water particles. Different type of interaction here though, because there are no ions this time. So up there in the sodium chloride situation, these are ion-ion interactions in the solid phase, and then ion-dipole interactions in the solution phase. And down there, for sucrose, these are dipole-dipole interactions in the solid phase, and then also dipole-dipole interactions in the solution phase. The dipole on the water interacts with the dipole on the sucrose. Now, this one down here does not conduct electricity because there are no ions, but the sodium chloride does conduct electricity. Let's take a closer look at the electrical properties of solutions. You'll discuss electricity quite a bit in physics, and so we're not going to cover it totally here, but let's mention a few things about it. We can say that an electrolyte is a solution that conducts electricity. Now, what is electricity? Electricity is when you have electric current. So electric current is a useful form of electricity in which charge flows along a wire. Right? A lightning bolt generates electricity, but it's not very useful. So if you can send electricity along a wire, then that's useful, and we call that electric current. So the way electric current kind of works is, I've drawn here a diagram of a battery with a wire going from the negative terminal through a light bulb all the way back to the positive terminal. Now, the negative terminal is a source of electrons. Electrons are generated over here, and the positive terminal is an electron sink in which electrons are absorbed. And that's what a battery is. You got one side that produces electrons and the other side that absorbs electrons, and so if you connect them with a wire, the electrons move along the wire from the anode, the negative side, to the cathode, the positive side. They're pulled along the wire. In fact, the electrons are running away from the other, electrons over here, and they're running towards, where there are no electrons, since they're being absorbed over there. And so it's the electrons that are moving along the wire. And if you put a light bulb in here, that's like a little thin portion of wire, and as the electrons flow along that thin portion of wire, the metal heats up because of friction, and it even glows when it gets really hot, and that's your old school light bulbs. So there you go. There's a little bit about electricity. Now, electrolytes are able to conduct electricity. Electricity passes through them. And so you can imagine this circuit being modified a little bit by the introduction of an electrolyte. So basically, over here, suppose you cut this wire and you see if the presence of the solution is able to bridge the gap, if it closes the circuit. And it does. What actually happens as the electrons are going along the wire over here, the positive ions in solution head to that location, and they annihilate each other. The negative ions and the positive ions sort of cancel each other off, and over there, on this terminal, the negative ions go to that terminal, and that produces negative charge on the wire, and so the negative electrons are then moving back to the cathode. You see, the presence of the ions allows the charge to keep moving along the wire. Now, this little interaction of what's going on here when the positive ions and the negative ions kind of, the negative electrons sort of cancel each other off, and over there where the negative ions produce electrons again. We'll talk more about those reactions in Gen Chem 2 near the end when we get into electrochemistry. It turns out that these are oxidation reduction reactions. So we mentioned them a little bit in chapter 4, or chapter, 4, actually, in chapter 4. So let me go back. There they are. At the end of chapter 4, we briefly talk about redox reactions, but we'll get into more depth in Gen Chem 2. But that's a redox reaction where electrons are absorbed and electrons are produced. But anyway, it's the ions in solution that allows the electrons to keep moving along the wire. And so charge passes through the solutions. The electrons go here, and then all of a sudden, there they are again. Okay? So the electrons move through the solution by the presence of the ions. All right? So in different solutions, there is sometimes, a very good ability for electricity to pass through, and other times not so good. And so there are solutions that can be considered to be weak electrolytes. So we should distinguish between strong electrolytes, weak electrolytes, and even non-electrolytes. Strong electrolytes are solutions that have a large concentration of ions, and they conduct electricity well. Weak electrolytes are solutions with a small concentration of ions, and they don't really conduct electricity very well. If you had a weak electrolyte in this circuit, the light bulb might be kind of dim. Okay? And then other solutions like sugar water, of course, they don't really have any ion concentration, and they don't conduct electricity. Let's look at some examples. Here's sodium chloride again. Okay, let's see here. So suppose we have 1 molarity sodium chloride. Now, sodium chloride is a soluble ionic compound which completely dissociates in solution. So again, if you have 1 molarity sodium chloride, we know that it dissociates into sodium pluses and chloride minuses in solution. And therefore, if you have 1 molarity of sodium chloride, you end up having 1 molarity of the cations and 1 molarity of the anions, because every one of these gives you one of those and one of those. So there are lots of ions in solution. All of the sodiums and chlorides are separated from one another in solution. Lots of ions. It's a strong electrolyte, and it would give you a bright light. Interestingly, some acids do this as well, and these are the strong acids. So for example, if you have 1 molarity hydrochloric acid in solution, this is a strong acid, and strong acids also completely dissociate. And when this dissociates, you have an H plus cation, that's a proton cation, and then the chloride anion. So that's what acids do, is they give you anions and cations, but the cation is always an H plus. Okay? And strong acids are the ones that completely dissociate in solution. So if you have a 1 molarity HCl solution, then that means, because every one of these gives you one of those and one of those, that means you have 1 molarity protons in solution and 1 molarity chlorides in solution. So all of the ions are separated from each other in solution again, just like the soluble sodium chloride. Okay, so again, lots of ions. We would call that a strong electrolyte, and that would also give us the bright light. So what about weak electrolytes? Well, an example of a weak electrolyte is hydrofluoric acid. If you have 1 molarity hydrofluoric acid, this is a weak acid, and it only partially dissociates in solution. So when you dissolve hydrofluoric acid in solution, you'll have a couple of H pluses and a couple of F minuses, but the vast majority of it dissolves as molecules. like 1 out of every 500 molecules might dissociate into the ions. You would write the chemical equation like this if you wanted to acknowledge that you do get some ions in solution, but not fully dissociated. It's not like all of this turns into that. This is like you would write a two-way arrow, and this represents what's called an equilibrium, where some of these molecules dissolve, okay, split apart, just some of them. And if you had 1 molarity hydrofluoric acid, you would have much less than 1 molarity protons and 1 molarity fluorides, because again, for every 1 mole per liter, you're going to have a lot less than 1 mole of the ions, so much less than 1 molarity of these. So you only got a few ions this time. That would be a weak electrolyte. It would give you a dim light bulb. And if you wanted to make that light bulb even dimmer, you might try 0.1 molarity hydrofluoric acid, or 0.01. So you can have an even weaker electrolyte just by cutting down the concentration. And finally, let's examine that sugar water again. So 1 molarity sucrose in water. This is a soluble molecular compound, but it does not dissociate because it's molecular compounds and it's not an acid. Okay. So when sucrose dissolves in water, all of the sucrose molecules split apart. There they are, but there are no ions. So this is a non-electrolyte, and the light bulb wouldn't turn on at all. So in summary, the strong electrolytes are soluble ionic compounds. So just being an ionic compound doesn't mean it's going to dissolve in water. But the ones that do, the ones that are soluble, are strong electrolytes, because when ionic compounds do dissolve, you get ions in solution. And also, so examples are sodium chloride, potassium iodide, silver nitrate, lots of other examples. But also, strong acids form strong electrolytes. And you should know what the 6 strong acids are: hydrochloric acid, hydrobromic, hydroiodic. That's our special state compound here, Hawaii. And nitric acid, sulfuric acid, perchloric acid. So all of these are strong acids, meaning when you add them to water, they fully dissociate. Okay, lots of ions. Weak electrolytes, these would include weak molecular acids like acetic acid, like that hydrofluoric acid we saw, chlorous acid, phosphoric acid. Lots of other acids are weak electrolytes, and they're the ones that only partially dissociate in solution. And there are also some weak molecular bases like ammonia, methylamine, and some other ones we'll talk about some other time. Weak electrolytes, you only have a few ions. So if you have 1 molarity acetic acid, you got a lot less than 1 molarity H pluses and acetate minuses. Okay, and then again, non-electrolytes are, if it dissolves, that might be a soluble molecular compound like glucose or sucrose or some other molecular compound. When it dissolves, there are no ions in solution, so non-electrolyte. Okay, in our next lecture, we will take a look at the compounds that do and do not dissolve in water. So what is the solubility of a compound, and then we'll use that information to describe precipitation reactions. So that'll be our next Chapter 4 lecture. Aloha.